Hi, I'm Swaroop Kotni, and today I'll be presenting our work Faastlane, which focuses on accelerating function as a service workflows. Function as a service is a new cloud application model where the developer is freed from managing the infrastructure. There are three stakeholders in FaaS: the developer, the cloud provider, and the client. The developer provides the function to the cloud provider, and the cloud provider returns an endpoint, say a HTTP endpoint, to the developer. The developer then provides this endpoint to the client to invoke the function. Each function request is executed in a container, and the cloud provider ensures auto-scaling of these containers based on request load. FaaS also provides pay-per-use billing, ensuring that the developers are charged only for function execution times. Typically, FaaS functions are expected to be stateless, and they're usually short-running. All the major cloud providers have a FaaS offering. For example, AWS has Lambda, and Microsoft has Azure Functions. While FaaS was originally envisioned that the execution of a single function happens on a single external trigger, for complicated applications to leverage FaaS, it was soon realized that one needs to put together multiple semantically related functions to capture application logic. And thus FaaS workflows were born. For example, AWS Step Functions allows one to create a workflow of FaaS functions. The developer can now leverage the auto-scaling and pay-per-use benefits of FaaS for more interesting and useful applications. For example, one can use FaaS workflows in inference pipelines. In the example that we show here on the slide, the developer can create an application that consists of three functions that are to be invoked in sequence. Like before, the developer provides these functions to the cloud provider, and the endpoint is informed to the clients. A client request triggers Lambda 1, and the output of Lambda 1 is sent as input to Lambda 2. Finally, the output of Lambda 3 is returned to the client. Note that each function in a workflow for a single client request executes in a separate container. Further, these containers can be scheduled on different physical machines on the cloud. Also note that the auto-scaling benefits of FaaS is retained across clients. For example, when another client B makes a request, the workflow functions can get scheduled on entirely different machines. Let us take a closer look at the interaction between functions in a single workflow instance. A workflow instance is defined as the set of all function invocations for a single client request. Consider the previous example of three functions in sequence. Each function executes in a separate container on a potentially different machine, and the intermediate results might have to go through a network stack or bear high software overheads to reach the next function in the workflow. We define the time taken in a workflow to communicate intermediate results as the function interaction latency. From our evaluation, we observed that the function interaction latency can go up to 96% of the total execution time of the workflow. We are not the first to observe this, and this is not a surprising observation given that the functions themselves are short-running. One of the previous works, SAND, observed that it is not necessary to execute functions of a single instance in different containers. In their solution, functions are co-located on the same machine, and each function is run as a process within the same container. The intermediate results are communicated using a local message queue. This design provides with a reduced function interaction latency, but we found that there's still significant scope for improvement. Faastlane borrows the idea of co-location from SAND and takes it a step forward by executing functions of a single instance as threads within a single process. The key benefit of doing this is that it enables functions to communicate via the fastest medium of communication possible, that is via loads and stores, over a shared virtual address space. In this example of three functions executing in sequence, upon a client request, the first function Lambda1 is launched. Lambda1 uses some part of the virtual address space to carry out function execution. Next, Lambda1 stores its output M in some other part of the virtual address space. The next function in the workflow Lambda2 loads the message M and then continues execution. Functions use some part of the virtual address space to carry out their execution, and some other parts of the virtual address space to transfer messages. The output of the last function, Lambda3, in this example is written as a response to the client. While this design is efficient for function interactions, it comes with its own challenges. The first is when one of the functions is malicious. Such a situation is likely in FaaS because developers often use third-party functions. Since the virtual address space is shared amongst all the functions, the malicious function can read memory regions that were allocated by other functions. Hence, one has to isolate functions even within a single workflow instance. To appreciate the need for isolation in a single workflow instance, let's consider the case of a healthcare analytics workflow, where a patient's medical records are used for analytical purposes. Here, the analytics function is an off-the-shelf function picked from an untrusted repository. Hence, before we pass the patient's records to the analytics function, we should anonymize patient's personal data such as name and occupation from the records. Personal data is denoted as protected health information or FI on the slide. Now, if an instance of this workflow were running on Faastlane, then the thread running the analytics function would have unrestricted access to the private data of FI identifier or anon records, both of which actually have access to the raw patient records. Hence, isolation even within a single workflow instance is a necessity. We found many such examples where isolation within a single workflow instance was required. Some examples could be protecting trade details in finance workflows or protecting model parameters in inference workflows. Now, our goal is to achieve low function interaction latency with lightweight isolation between functions within a single workflow instance. To provide such isolation, Faastlane begins with managing the virtual address space at the granularity of pages. With Intel's memory protection keys, or MPK, that is widely available in Intel Xeon processors, each page can be tagged with a protection key. The read-write permissions to a protection key can be read from a register called the PKRU register, and the value in this register can be modified using a user space instruction. Faastlane assigns a unique protection key to each thread. Whenever a thread requests for memory, a custom memory manager allocates from a page that is tagged with the protection key of the thread. Next, we have shared protection keys so that all threads can read and write from pages tagged with the shared keys. These pages are used for interactions between component functions. Now, in this example, we will use 5 protection keys, 3 private keys, 1 for each thread, and 2 shared keys, 1 for communicating with the client and 1 for function interactions. When a thread begins execution, Faastlane modifies the value in the PKRU register to only allow access to shared protection keys and 1 extra protection key that is unique to the thread. For example, when lambda 1 is running, Faastlane has access to exactly 3 keys. All the memory requested by lambda 1 is served from pages tagged with the private key of the thread. The output of lambda 1 is written to a page tagged with a shared key so that lambda 2 can read from this page. Before lambda 2 is invoked, note that the PKRU register is set such that the memory allocated by lambda 1 is no longer accessible. The same strategy is followed when the workflow transitions from lambda 2 to lambda 3. The output of lambda 3 is written to a shared page and can be sent as a response to the client. Now consider the case when lambda 2 is malicious. When lambda 2 was executing, the value of the PKRU register was such that the thread cannot access lambda 1's private data. Any attempt made to read or write from the malicious thread is denied by the page protections guaranteed by MPK. Hence, our goal of low function interaction latency is achieved via hardware enforced isolation. Now that the isolation problem is solved, we found out that there is one other problem that can hamper the performance of some of the workflows on Faastlane. A huge majority of FaaS functions are written in interpreted languages such as Python and Node.js. These languages disallow parallel thread execution because of a global interpreter lock. Using threads in these languages can lead to underutilization of hardware available to the function. The global interpreter lock ensures that only one thread within a process runs inside the interpreter. Thus, in workflows exhibiting parallelism, only one function within the workflow will be running at any point, slowing down the workflow. Hence, executing functions in threads all the time is not the best solution. Interestingly, there are many workflows that exhibit parallelism. One such example can be found in the financial industry. The Financial Industry Regulation Authority, or FINRA, has been known to utilize AWS step functions. FINRA ensures the integrity of financial markets by auditing the financial records of its customers. In FINRA, a single transaction must go through hundreds of audit rules, each of which can be run in parallel. Using a thread-based solution in this case will limit the number of audit rules running in parallel to 1, thus leading to a very high end-to-end latency. To understand Faastlane's design for parallel workflows, let's consider a sample workflow with 4 functions. Lambda 2 and lambda 4 can be executed in parallel once lambda 1 finishes, and lambda 3 aggregates the results of these parallel functions. To begin with, lambda 1 executes as a thread in process 0. Once lambda 1 finishes, lambda 2 is launched as a thread in process 0, but lambda 4 is launched in a separate process within the same container. Launching lambda 4 in a separate process eliminates the GIL problem because each process had its own interpreter, ensuring that both functions can now run in parallel. Lambda 4's output is made available to process 0 via shared memory. Once both the function's outputs are available in process 0, Lambda 3 gets triggered and its output is sent back to the client. So we overcome the problem of GIL in interpreted languages by running functions as processes instead of threads wherever there is parallelism in the workflow. In the previous example, we ran two processes inside the same container, assuming that they will be run in parallel. However, this will require the container to have at least two vCPUs. In cases where the hardware parallelism available inside a container is limited or less than the parallelism required in a workflow, Faastlane launches functions in the parallel stage of a workflow on separate containers rather than processes. These functions can get launched on any other machine. In such cases, the function interactions will grow larger due to network delays, but Faastlane is able to utilize hardware parallelism across machines when necessary. Hence, Faastlane minimizes function interaction latency using loads and stores, while also leverages hardware parallelism wherever required. To put it all together, the developer provides component functions along with the workflow description to Faastlane. Faastlane's workflow composer decides to launch threads, processes, or containers based on the description of the workflow and sends the output to the cloud provider. At runtime, Faastlane's thread-level memory manager, along with Intel MPK, provides lightweight isolation among functions launched as threads in a workflow instance. In the entire lifecycle of workflow deployment through Faastlane, we expect no new information from the developer. Let's move on to the evaluation now. We evaluate Faastlane on an Intel Xeon machine with 36 cores and 384 GB RAM. Coming to the software, we used an unmodified version of OpenWhisk. We deployed our thread-level memory manager inside the running containers on OpenWhisk and allowed Intel MPK related system calls. For comparison, all the computing frameworks were run locally, except for AWS step functions, which is run on an AWS cluster. First, we quantify how much does Faastlane reduce the function interaction latency compared to the other platforms. The y-axis shows what percentage of the end-to-end latency is through function interaction latency. Please note the log scale. First, AWS step functions has a very high function interaction latency. As discussed earlier, intermediate state travels through the network stack or bears high software overheads leading to very large function interaction latency. Functions in OpenWhisk communicate using Kafka queues and the overheads are still high. SAN performs better than step functions and OpenWhisk in most cases, given it co-locates functions inside a container. Faastlane spends at most 1.6% of total execution time on function interaction latency. This is significantly better than other platforms because communication is via loads and stores wherever possible. Note that the percentage function interaction latency of step functions in FINRA is smaller than Faastlane. This is because the end-to-end latency in step functions is very high. In terms of raw numbers, Faastlane performs better than step functions even in the case of FINRA. Next, we show how achieving low function interaction latency improves the throughput of the FaaS platform. The y-axis plots the number of requests that can be served within a minute. We show AWS step functions here for the sake of completion, but the numbers are not directly comparable since the execution is not on a local deployment. Note that the throughput of ML prediction service on OpenWhisk is very low. This is because the size of the state transferred between functions is high, and the workflow uses AWS S3 to transfer state. Comparatively, SAN performs better, providing higher throughput in most cases. Faastlane beats the rest of the competition in all the workflows. Overall, Faastlane has up to 16 times higher throughput compared to OpenWhisk and is up to 49% better than its closest competitor, which is SAN. Our paper further evaluates all our design choices, dollar cost of execution, scalability across machines, and so on. To conclude, function interaction latency is a key contributor to the end-to-end latency in FaaS workflows. Faastlane minimizes the function interaction latency by launching workflow functions as threads of the same process. It uses memory load store instructions for function interactions. Faastlane uses Intel MPK to provide lightweight isolation amongst component functions within a single workflow instance. And it dynamically chooses to launch processes instead of threads to leverage parallelism within workflow instances. Finally, Faastlane provides all these benefits by being transparent to the developer. That brings us to the end of the talk. Please feel free to reach out to any of us in the contacts.